baton to Sharad. So can you tell me when we are, I'll be taking a very literal question, a very fundamental question here, Sharad. I can understand clustering. I can understand supervised algorithms. I can understand probably even recommender systems where we would want to, have some hyperparameters to improve it. What is there in dimension reduction? We're just reducing the dimension. What is it? Why do we need hyperparameters? Could you probably start from there and then, take it over?
Thank you, Nitin, and welcome back to the channel, everyone. Hope you're enjoying and learning along the way. The series of discussions that we're having as part of this YouTube live sessions should eventually help you to land up into a job. Based on our experiences, we are trying to bring out all those questions which probably might come in your interview. So hope everybody is taking a key note of all these sessions, and let me jump into the question. The question was basically with respect to dimension reduction, which is a little tricky subject in the entire data science world, data science world, but very essential. And we basically need to try and improve the algorithm's performance, for example. Obviously, we need to work with a limited or small size of data. But saying that, we cannot reduce your data as part of your Wilson fancies, right? We cannot just reduce the data. So in order to extract the information, we from the given set of features, we try and use this dimension reduction, which also works as feature selection algorithms. And the hyperparameter with respect to these algorithms, right, is the component itself, the number of components itself. So when you say dimension reduction, for example, if I have 10 columns, let me share my screen and show you the hyperparameters, the functionalities and all that, right? So I've just pulled up the document for you people. And if you look at this, this is the PCA algorithm, right? And I'm trying to show this. And by the way, you can access these file on the website, 360DigitMG website itself, so that it helps you to quickly remember all the things from your practice perspective. Like I've shown in the previous sessions, it will be available on 360DigitMG website in the learning resources. At the end of the session, anyways, I'll again walk you through with the navigation. Now, let us talk about the dimension reduction here. And we are trying to talk about a popular algorithm, which is principal component analysis. Like any other algorithm, you can see that there are a bunch of parameters that we can pass through to control how the algorithm actually does the entire component analysis and then tries to compress your features. The most important feature that we talk about is the number of components itself. Without the number of components that you're going to pass, there's no compression, right? What will you do with taking the same number of columns? If I have 100 original columns, and if you do PCA, and if you again get same 100 columns, 100 PCs, then there's no point in achieving this or implementing this logic. So what should be the number of principal components that you want to get this information compressed to? So that itself is the first hyperparameter that we need to pass. And it is going to define the entire algorithm's performance on this data. So for example, if I have a data set given to two people, let's say person A and person B, I'm giving 100 columns data for both these people. Now, let's say person A is implementing PCA itself, but the person decided to get 20 PCs. Whereas person B tried to compress the data with only 10 PCs. The difference between the data points is the dimension itself, right? So here you will have 20 columns, you will have 10 columns after transformation. But when you're using this data set for any machine learning algorithm, you can very clearly say that the time taken for person A's data set would be a little higher than the time that we take for processing the data that we obtain from person B's analysis. Because of obviously the dimension is reduced. So computation becomes much faster. Remember, the trade-off is always there. The accuracy will come down, but still, depending on what is your business objective, you might want to subjectively decide on which compression you want to achieve. So that is the first hyperparameter that we talk about. Likewise, we have a lot of other parameters, like you have your copy. This is one of the hyperparameters that we have here. Right? If by default it is true, but what we are doing is, if it is set to false, the data that is being passed to fit will be overwritten. That means you're going to get the transformed data, right? Original data will be overwritten. So this is not going to impact much, but this is also one of the parameters. Do you want to show original data also, or do you want to just see the transformed data, right? So that is one of the options. Likewise, you can see various other options. You can deep dive into each of these options and then try and experiment, depending on the time frame that you have for your project. Nitin.
Yeah, thank you. Apologies, friends. I was having a slide. Yeah. So thank you, Sharad, for that detailed response. And I especially like the illustration, you made about the people. It's very interactive and nice. So yeah, Bharani, can you, tell me about the same thing? My question was basically, firstly, your take on the question. The question being, why do we need hyperparameters when it is a simple dimension reduction? And what does the hyperparameter really do in as far as dimension reduction algorithms are concerned, generically speaking, not specific to any algorithm? That was my question. Could you please give your insights on that?
Sure, absolutely. If you may just allow me a minute, because I want to pull up the maybe mind map and explain a few things quickly. So this will probably make things interesting here. So first of all, we need to get started with unsupervised learning techniques. This is what I keep telling to people, that you get started with unsupervised learning techniques and then try to apply supervised learning techniques on top of that. And even among the various unsupervised learning techniques, you will have to, do a mix and a match. Probably in topic mining, in text mining, you'll use clustering, or you'll use dimension reduction techniques such as SVD, right? Which is very similar to LSA or, LSI that we have. And I will quickly take a minute here to show something interesting. Okay. So let me share my screen and explain here. So when it comes to dimension reduction techniques, the first point that you need to think about is, which algorithm do I need to use? When you have data which follows linear patterns, then we have LDA, we have NMF, we have ICA, SVD, PCA, factor analysis, so on and so forth. And each of these work in a different manner. Each of these have a different way of working. And we also have we will also have nonlinear patterns in the data. When you perform your exploratory data analysis, You'll figure out whether your data are non-linear in fashion or linear in fashion, etc. And if you have non-linear data, then for a pattern, then you employ SNE or TSNE. These are the techniques which work very well. Okay. And these techniques work very well when you have textual data. Textual data, you cannot, imagine it as a linear problem. So when you have textual data, it will have very high dimensions, too many words to deal with, etc. So this is how you figure out. Figuring out which algorithm works well is point one. Point two is thinking about or understanding what are the various hyperparameters. And already we have discussed multiple times that hyperparameters are those options which you can change and experiment with. For example, Sharad was talking about number of components. A number of components can be any value, but in interviews, questions could be around what is the minimum value and what is the maximum value when it comes to number of components in PCA. Minimum, you can have one, obviously. And the maximum would be number of features. You cannot exceed the number of features. That means in your input data, if you have 20 inputs, then the maximum number of principal components that you can have would be 20. PC1, PC2, PC3, the maximum that you can have is 20. Okay, so this is the reason why we need to understand the hyperparameters. Okay, this is one thing with respect to PCA, but I'm sure we'll delve deeper into the other, dimension reduction techniques, and we'll understand more on that front as well. And here we have another thing which is called as iterated power. We have n underscore oversamples, right? So we have TOL, which is tolerance level, SVD solver. So all of these things are interrelated. Okay, though we are talking about principal component analysis, you might see references pertaining to SVD because both of these are going to work on the basis of linear algebra. So the underlying working more or less remains the same. Okay, and we also have SVD. Here also, we have a bunch of hyperparameters which exist. And here also we have, number of iterations, number of oversamples, right? Tolerance level, algorithm, number of components. While we have umpteen number of hyperparameters, it's humanly not possible to remember each and every hyperparameter. However, the most important hyperparameters one has to remember. And if you ask me what is the single most important hyperparameter, both with respect to PCA and SVD, then I would say it'll be number of components. Okay, and this SVD concept is, very well explained as part of topic modeling techniques such as LSA, which is also called as LSI, and also LDA. Sometimes people also call this SVD as LSA or LSI. Interchangeably, they use that. That is how closely they are related. And when we are using SVD to deal with text data, then we need to use 100 as your number of components. Okay, so that's the recommended value. Because in LSA, it's all about topic modeling. How many topics exist in a textual document is what LSA will help you figure out. Okay, so in that way, there are a bunch of things. So these are a few things that I wanted to talk about.
Yeah. Thank you. Thank you so much, Bharani.